Hello students, this is Professor Chalai, and in this video we're going to look at thermal energy, temperature, and heat. As always, you can follow along with our Chapter 5 workbook. By the end of this video, you should be able to define energy, heat capacity, and the specific heat capacity, and you should be able to perform different calculations using the specific heat capacity. Let's get started. So in our previous lecture, we looked at energy and energy units, and one of the types of energy that we talked about was kinetic energy, or hopefully that you read up on was kinetic energy, where you learned that kinetic energy is energy associated with motion. Another kind of energy that's associated with motion is thermal energy. So if you imagine molecules, whether it's a single atom or two atoms bound together or multiple atoms bound together, these atoms are not fixed. They're always in motion. They're always vibrating. So I'm going to represent that by little squiggly lines. These molecules are always vibrating. They're never still. And it's that motion of the atoms in molecules that give it what we call the thermal energy. So thermal energy, the definition is the kinetic energy associated with the random motion of atoms and molecules. So if something has higher thermal energy, you can imagine those molecules are vibrating much more vigorously. They're zipping around, moving about much more vigorously, as compared to something with lower thermal energy, where the molecules should be not moving as vigorously. Okay, so temperature and thermal energy, as you might guess, are very closely related. In fact, temperature is just a quantitative measure of how hot or cold a substance is. So if you think about it, we can't really go in there and measure the motion of every single molecule or atom, but the temperature gives us a sort of general idea of the thermal energy that a molecule or a system of molecules contain. And so that brings us to heat. And heat is just the flow of thermal energy. So heat, represented by the symbol Q, is the transfer of thermal energy between two bodies at different temperatures. So we might think of heat as just being something, whether something's hot or cold, but really that's the temperature. Heat is a movement of thermal energy from something, between two things of different temperatures. It always flows from the substance of higher temperature to the substance of lower temperature. So that's heat. It's the flow of thermal energy. And so that brings us to this idea of exothermic and endothermic processes that you may have heard of. An exothermic process is a process that releases thermal energy, or heat flows outwards from the system. So exothermic, this will be a process that releases heat, whereas endothermic is a process that absorbs heat. And later on in this week, we'll look at exactly what we mean by exothermic and endothermic when we look at different types of heat transfers. Now, we talk about heat flowing between substances of different temperatures, but how can we measure exactly how much heat flows? Well, let's think of a system. If you have, let's say, a cup of water at I don't know, 25 degrees Celsius. That's room temperature. And you add heat to this system. It's my little fire. You add heat to the system such that it increases to, let's say, 30 degrees Celsius, right? You take the same setup and you add heat such that it increases to, I don't know, 50 degrees Celsius. Clearly, in the second case, you've added more heat. So the heat then is related to the temperature change of the substance, right? So the smaller temperature change means you added a smaller amount of heat. The larger temperature change means you add a larger amount of heat. So the heat that we said is represented by the letter Q should be proportional to the temperature change. Let's represent that by a delta T. Delta, Greek letter delta, usually represents a change. So delta T means the change in temperature. And the way we're going to define the change in temperature is just the final temperature, the final, minus the initial temperature. So the final temperature means the temperature you end up with. The initial temperature means the temperature that you started with. And so in this example, the final temperature will be either 50 or 30. And the initial temperature will be what you started with, 25 in this example. So the heat will be related to the change in temperature. The larger the temperature change, right, the more heat you added. The smaller temperature change, the less heat you added. And remember earlier in the semester I mentioned that proportional symbol here simply means that Q is equal to some constant multiplied by the whatever value we had here. So Q will be equal to some constant times the temperature change. And this constant we call the heat capacity, sorry. That constant C we'll call the heat capacity. And so we have that repeated here. The heat is equal to that heat capacity times the temperature change. So for definition, the heat capacity is simply the amount of heat needed to raise the temperature by 1 degree Celsius, right? So heat is typically measured, it's in joules. Temperature, we're going to measure in degrees Celsius. And so to make the units cancel, the units for heat capacity should be joules divided by degrees Celsius, right? Such that degrees Celsius will cancel out and we're left with joules in the answer. So that's heat capacity. It's measured in joules over degrees Celsius. So let's put that here. The units will be joules divided by degrees Celsius. Okay, sometimes you'll see that this is written in terms of joules over Kelvin. In this case, they're both the same, right? A temperature change in degrees Celsius is the same as a temperature change in Kelvin. All right, but now let's think about this. We talked about using the same amount of water, and if you heat it at a higher temperature, you use more heat. But let's look at a different example using the same idea. Let's say you have a kettle for some tea, and you want to boil this from 25 degrees Celsius to boiling 100 degrees Celsius. You will use an amount of heat. What if you have a whole big pot of soup that you're making? And you want to boil this starting from 25 degrees Celsius all the way to 100 degrees Celsius. You might be thinking, yes, in the second case, you would need to add more heat to boil a whole big pot of water than it is to boil a small kettle of water, right? Even though the temperature changes are going to be similar. So we need to add something else to the equation to account for the amount of substance we're dealing with. You want to boil a small kettle versus a large pot. Those are very different because the amount of water is different. And so to account for that, the amount of substance that we're dealing with, we'll call that the specific heat capacity. The symbol is C subscript S. And there we change C into M times Cs. So remember the heat capacity equation is Q is equal to C times delta T. Well, we want a way of adding in the mass in that equation because the mass gives us a measure of how much stuff we're dealing with. And so we'll break that C up into M times Cs, and that we'll call that the specific heat capacity. And in terms of units, right, heat is still measured in joules, mass is measured in grams, the temperature change is measured in degrees Celsius, and so to have the units cancel out, the specific heat capacity should have units of joules divided by grams times degrees Celsius. And that way, the grams from the mass will cancel out the grams in the specific heat capacity, and the temperature will cancel out the temperature. So that's the specific heat capacity. This is more useful because the amount of stuff that you're increasing the temperature of matters. And that value of the specific heat capacity is very, interestingly enough, specific to the type of material that you're looking at. For example, lead has a value of 0.128 joules per gram per degree Celsius. Gold has a specific value, granite has a specific value, and so on and so forth. Water has a specific value, and that will come up a lot. So if you can find the specific heat capacity of some material, you can compare it to this table to figure out what that material is, even if you don't know what the material is to start with. So here's a table of just some common materials that we're going to look at for different questions. So now that I've gone over the introductions of heat capacity and specific heat capacity and their equations and their units, I would like you to try numbers 2, 3, and 4. You can attempt these by yourselves to begin with. I will certainly go over these calculations in detail for you, but I would like you to pause and try them for yourself first. That's always a good practice. Okay, let's look at number 2. Number 2 says you have a flask containing 8.0 times 10 to the second grams of water. So it tells us the material, it's water, and the mass, it's 800 grams, and it's heated. It tells us the temperature of the water increases from 21 degrees Celsius to 85 degrees Celsius. So let's write these down. So the mass is 8.0 by 10 to the second grams. 21 degrees Celsius is what we started with, so that's the initial temperature, 21 degrees Celsius. The final temperature is 85 degrees Celsius. And the question is, how much heat did the water absorb? So as I mentioned, it also tells us the material. It's water. So the specific heat capacity of water, H2O, is from this table, 4.18 joules per grams per degree Celsius. So 4.18 joules per gram per degree Celsius. The question is, how much heat did the water absorb? So the question is asking us to solve for Q. So let's set up our equation. We know that Q is equal to mass times the specific heat capacity times the temperature change. We haven't calculated the temperature change yet, but we have the starting temperature and the ending temperature. So the temperature change will be the ending temperature, 85 degrees Celsius, minus the starting temperature, 21 degrees Celsius, which gives us 64 degrees Celsius. So let's plug those numbers in this calculator, into this equation. So the mass was 8.0 by 10 to the second grams. The specific heat capacity of water is 4.18 joules per gram per degree Celsius. And the temperature change was 64 degrees Celsius. So degrees Celsius cancels out with degrees Celsius over there, and grams cancel out with grams there. So we're left with joules for the heat units, which is exactly what we want. You plug all of these into our calculator, and we'll get 214,016 joules. We need it to 2 sig figs, 3 sig figs, 2 sig figs. So our answer needs to be in 2 sig figs, which will be 210,000 joules. And that's it. That's our answer. Now, in a lot of chemistry problems, when we express our answers in joules, we'll get a very large number. And because we don't like to write so many zeros every time that we write our answer in joules, oftentimes you'll see the answer written in kilojoules. Remember, a kilojoule is 1,000 joules. So in kilojoules, this will just be 210 kilojoules. Either of these answers will be correct because the question didn't specify what units for you to use. But all it needs to be is in 2 sig figs, which it is. Okay, try to answer number 3 on your own if you haven't already done so. Pause the video and then I'll go through it together. Okay, number 3 is very similar. It asks for the amount of heat in joules this time, so it specifies. It gives us the mass of the substance, 503 grams. It gives us the material. It's an iron skillet, right? So it's made up of iron. And then it gives us the temperature change. It increases its temperature starting from 25 degrees Celsius to 250 degrees Celsius. And this question is even nicer. It gives us the specific heat capacity of iron. We didn't have to go look it up in the table. So we know their equation, the heat is equal to the mass times the specific heat capacity times the temperature change, right? The mass is 502 grams. The specific heat capacity is 0.449 joules per gram per degree Celsius. And the temperature change will be the final temperature, 250 degrees Celsius minus 25 degrees Celsius, which is 225 degrees Celsius. Now, we should technically write this as 230 degrees Celsius rounded to the tens place because of sig figs. Okay, so then we can plug those numbers in. Q is equal to the mass, 502 grams, multiplied by the specific heat capacity, 0.449 joules per gram per degree Celsius, multiplied by the temperature change, 230 degrees Celsius. And that means that grams cancel with grams and degrees Celsius cancel out with degrees Celsius. And so what we're left with, if you punch all of this into your calculator, would be about 51,000 joules. Rounded to 2 sig figs because we have 2 sig figs there. Okay. Hope we all got that one correctly. Let's look at number 4. If you haven't tried this already, please try so now and then we'll work this out. So here we have a student who found a shiny gold-colored rock and they want to know whether it's actually gold. So they decided to measure the heat capacity, and this is an experiment that we can perform. So first you weigh the rock and you find it has a mass of 4.7 grams. So let's write that down. The mass is 4.7 grams. Okay. Then you absorb 57.2 joules of heat, right? So the heat, Q, is 57.2 joules. And the temperature increases from 25 degrees Celsius to 57 degrees Celsius. So the temperature change will be 57 degrees Celsius minus 27 degrees, minus 25 degrees Celsius. There we go. 25 degrees Celsius, which means that the temperature change is 32 degrees Celsius. Okay, so let's write our equation. We know that Q is equal to M times the specific heat capacity times the temperature change. We know the heat, we know the mass, we know the temperature change. Let's find the specific heat capacity. So to do that, I'm going to rewrite this equation using some algebra to make it easier to solve. So if we divide this side by delta T, that will cancel out, and we divide this side by delta T. And if we divide the right-hand side by M, such that the M cancel out, we'll divide the left-hand side by M. So that means that the specific heat capacity should be equal to the heat divided by the temperature change times the mass. So let's plug those numbers in. The heat was 57.2 joules. The temperature change was 32 degrees Celsius. And the mass was 4.7 grams. We should plug all of this into our calculator and we get to two significant figures, 0.38 units of joules over grams over degree Celsius, so joules over per gram per degree Celsius as our answer. Now the final question is this consistent with being pure gold? So let's look at our table. Pure gold would have a specific heat capacity of 0.128 joules per gram per degree Celsius. That is not what we got. We got 0.38 joules per gram per degree Celsius. So we can conclude that the student did not find gold, but what did they find instead? Let's look at all of the values. That number is very close to what we have for copper. So then we can conclude that, hey, the student, by performing this specific heat capacity experiment, actually found copper and not gold. And that's how specific heat capacity can be used to identify materials. All right, I hope this all makes sense. In our next video, we'll look at calorimetry. I'll see you then. Bye.